Today we're going to prove a pretty gnarly looking algebraic identity. And I think the takeaway here is sometimes problems don't look very fun, but it's always important to practice lots of different techniques so you become a well-rounded problem solver. So in particular, we've got this product of three terms on the left-hand side. We have the square root of a plus c times b plus c minus c, the square root of a plus b times a plus c minus a, then the square root of a plus b times b plus c minus b. Then on the right-hand side, we have a quotient. So this is 2 times a plus b plus c plus a plus c. And then we have this denominator here, which is the square of the square root of a plus b plus the square root of b plus c plus the square root of a plus c. But let's notice there's a more compact version of this identity, which is given by this so-called cyclic permutation of a, b, and c. And by a cyclic permutation, I mean that we evaluate or we look at this expression on one side, is we look at one version of this expression, and then we replace all of the a's with b's, all of the b's with c's, and then we generate another part of the expression, and then we do that one more time to get another part of the expression. And over here we say we're doing the product, whereas over here we're doing these sums. So I haven't subscripted these sums with this cyclic permutation, but that's what's going on here. So keeping that in mind, I think there's a pretty easy way to write this down in general, and that would be something like this. Let's say we take the product over some sort of permutation that goes a1 gets sent to a2, which gets sent to a3, which gets sent to a4, all the way around we have an, which is sent to a1. And then we'll have the square root of, we'll have a1 plus a2 times a2 plus a3, and then minus a2. Okay, and then over here on the right-hand side, we'll have 2 times the sum of, let's see, that looks like a1, a2, and then we're taking that cyclic permutation there. So the first term in that sum will be a1, a2, but the second term will be a2, a3. The third will be a3, a4, so on and so forth. And then down here in the denominator, we'll have the sum of the square root of a1 plus a2 quantity squared. And that's the first term. Under this cyclic permutation, the next one would be a2 plus a3. And then, like I said, so on and so forth. Notice that's generating this same kind of thing that we have up here. Now, one thing that might be typical to do would be to look at a version of this identity here where we have fewer variables than our goal identity. But in that case, it's not super possible without modifying things maybe until it doesn't really look like the identity, which is a goal, and that's because this left-hand side has a general setup that involves a1, a2, and a3. In other words, it involves 3 terms in a row. So that means if we were to look at the n equals 2 case, then a3 would be the same thing as a1, which probably would generate some very obvious formula. Let's see which formula that would generate. So like I said, we're going to look at the n equals 2 case, although we expect this not to be super interesting. So in other words, this given formula is the first interesting version of this. Okay, so let's see what happens to this left-hand term. Here we'll have 2 terms from this product. One before we switch a1 and a2, and one after we switch a1 and a2. Keeping in mind that we're making the simplification of a3 to be a1 here, just so that it kind of lines up as best as possible with what we have here. Okay, so that means the first term of this product will be the square root of a1 plus a2 times a2 plus a1, and then from that we subtract a2, and the second term of that product will be the square root of a2 plus a1 times a1 plus a2 minus a1. But notice that simplifies quite a bit. So here we're taking the product of two of the same terms and then taking their square root. So we simply have a1 plus a2, and then we subtract a2, so that turns into a1. And for the second term, we'll get a2 for similar reasons. Okay, so like I said, that's the left-hand side. Now let's see what the right-hand side looks like, just to make sure that this works in the n equals 2 case, which is not guaranteed. This identity could not hold in the n equals 2 case. In fact, it may only hold in this n equals 3 case. Okay, so like I said, the n equals 2 case will be 2 times, well, this is going to be a1 times a2 plus a2 times a1, based off our cyclic summation there. And then let's see what this will be. So this will be a1 plus a2, taking the square root, and then plus the square root of a2 times a1, and then taking the square root, and then we have to square that whole thing. But now let's notice what happens when we simplify. Here we're adding these two terms together and then also multiplying by 2, so that gives us 4a1 a2. And then in the denominator we'll end up with 4a1 plus a2. Okay, so then we can cancel the 4's and we get a1 times a2 over a1 plus a2. So I think it was a good exercise to see what this tried to collapse to in the n equals 2 case. Under the interpretation that we made, notice this is naturally written for at least 3 variables. But notice it does not hold under our interpretation of this collapse to n equals 2 case. Maybe before we move on to proving our identity up here, can you think of a version of this identity for 2 variables? Okay, now let's get to proving our identity. Okay, so now let's get into our identity. So notice we've got this kind of stuff under square roots, a plus c, b plus c, and a plus c. So it makes sense to try to get rid of those square roots. So maybe we'll do a change of variables where we set each of these sums equal to a perfect square. And that's exactly how we'll start here. So let's maybe set x squared equal to b plus c. And then likewise, we'll have y squared equal to a plus c. And then we'll have z squared equal to a plus b. So that's already going to simplify these square roots on the left-hand side. But let's also notice that we'll need these free a, b's, and c's as well, because we have to take that difference there. So we can do a fairly simple method of solving this system of equations for a, b, and c. I'll leave that off, but what you'll end up with is the following. So this leads to a is equal to 1/2 times the quantity minus x squared plus y squared plus z squared. And then we'll have b is equal to 1/2 times the quantity x squared minus y squared plus z squared. And likewise, we'll have c is equal to 1/2 x squared plus y squared minus z squared. Like I said, this is just from inverting this substitution that we've just made. Okay, so now let's keep that in mind. And now I'll take maybe this left-hand side of the equation and I'll set that equal to the left-hand side. So I'll just set that equal, so I'll denote that as LHS. So here's what we have. This all implies that the left-hand side now looks like, well, let's see, this square root of a plus c times b plus c will simply be x times y, given that those are x squared and y squared. Okay, so that's going to be x times y, and then we'll have minus c, but that'll be minus 1/2 x squared plus y squared minus z squared. So I'll write that down. Great. And then we'll have similar things for the other 2 terms of this product. So let's get those on the board really quickly. And there we have it. So now I'm going to factor 1/2 out of each of these terms, but that'll be like factoring a 1/8 out of the whole thing. And that'll also deposit a coefficient of 2 here for xy, yz, and xz. So here I have 1/8, and then I'll be left with 2xy minus x squared minus y squared plus z squared after multiplying some things out. And then similar things for the rest of these two terms. So 2yz, and then plus x squared minus y squared minus z squared, and then 2xz, and then minus x squared plus y squared minus z squared. So something like that. And now let's look closely at what's happening for this first term. Here we have this 2xy along with minus y squared minus x squared, or minus x squared minus y squared. And let's notice I can factor a minus sign out of that, and I'm left with x minus y quantity squared. So let's see, if we multiply that out, disregarding this minus sign, we'll have x squared minus 2xy plus y squared, but then negating everything gives us what's going on down here, you know, in the big term here. Okay, so now we can do similar things for all of these other terms. So let's see. This orange overline will turn into negative y minus z squared. And then finally this red overline will turn into negative x minus z squared. Okay, good. So now let's rewrite that using those observations. So we've got an eighth, and then we'll be left with z squared minus x minus y quantity squared. And then here we have x squared minus x minus z quantity squared. And then finally we have y squared minus x minus z quantity squared. So this is shaping up. But now notice each of these are differences of squares. We have a perfect square minus a perfect square in each of them. So that just begs us to do a factorization of perfect squares. So let's do that for each of these. So for this first one, we'll have z minus x minus y, but that's going to be z minus x plus y after distributing the minus sign. And then we'll have also z plus x minus y, so z plus x minus y. Okay, so let's maybe spread that out here just so that we can see what happened. This is z minus x minus y times z plus x minus y. I just went ahead and I distributed that minus sign. And then we'll have similar things for the rest of these, so let's get those on the board. Okay, there we have it. But now let's notice we've got some like terms. So this magenta overlined object is exactly the same as this magenta overlined object. Similar, this blue overlined term is the same thing as this blue overlined term, and these two red overlined terms are exactly the same. So that allows me to write those as squares. So let's see, we'll have z minus x plus y quantity squared, and then z plus x minus y quantity squared, and then finally x plus y minus z quantity squared. And I'm actually going to multiply by one more term in the numerator and the denominator, and that's just to like even all of this out. And that will be x plus y plus z quantity squared. And then I need that downstairs as well. So we'll have 8x plus y plus z quantity squared. But notice that x plus y plus z quantity squared will be exactly what we have in the denominator over here. So we're also looking towards our goal. Okay, so now let's bring this expression up and then we'll keep going. Okay, so this is where we left off. And now I'm going to take two pairs from these four terms in the numerator and combine them. So, and those will be the two exterior terms, so these two that I'm overlining in magenta, and these two interior terms. And then let's see what is different about those. So we have y plus z minus x, and then y plus z plus x for the magenta overlined terms. So those will multiply together like a difference of squares, so that'll be nice. And then let's see what we have here. We have x we have x minus the quantity y minus z, and here we have x plus the quantity y minus z. So let's maybe spell that out a little bit more carefully for this term. We'll think about this as x minus the quantity y minus z. So that means those two paired objects will multiply to differences of squares. So let's see. In the numerator, we will now have y plus z quantity squared minus x squared. That whole thing is still squared. And then we'll also have, let's see what this is. It'll be x squared minus y minus z quantity squared. Again, that whole thing is still squared. And then we still have this 8 times x plus y plus z all squared in the denominator. Okay, so, and then we can expand this out, and we could have done this before, but writing it like that, this makes the expansion a little bit simpler. And what we'll end up with is the following. So this will give us 2x squared y squared plus 2y squared z squared plus 2x squared z squared, and then minus x to the fourth minus y to the fourth minus z to the fourth. And this is all squared, and over this kind of denominator we've been keeping around, 8 times x plus y plus z all squared. And then let's peer into what each of these things look like. So let's put a green overline here, and then we'll expand this out. So since x squared is b plus c and y squared is a plus c, then here we will have 2a plus c times b plus c. Okay, and then let's expand the rest of these out as well. So for this yz, we'll have something like this. It'll be 2a plus b times a plus c. And then next up, for this x and z term, we'll end up with, let's see, 2a plus b times b plus c. Okay, great. And now let's look at what each of these things expands out to in turn. So this will give us 2, let's see, we'll have a times b, so ab plus 2, let's see, a times c plus 2, b times c plus 2c squared. So that's what that green one expands out to. And then let's see what this magenta one expands out to. So we'll have 2a squared, and then 2ab, and then 2ac, and then 2bc. And then likewise, this blue one will give us 2ab plus 2bc plus 2ac plus b squared. So we're left with something like that. And then in turn, let's look at these as well. So here we'll have this minus x to the fourth will be b plus c quantity squared. So I'll go ahead and write that out as minus b squared, and then minus 2bc, and then minus c squared. And then let's see, next up will be this minus y to the fourth. So that'll give us a minus a squared minus 2ac minus c squared. And then finally, this minus z to the fourth will give us minus a squared minus 2ab minus b squared. So we're left with something like that. And now let's see what we can cancel. So this minus a squared, this minus a squared will cancel with these 2a squareds here. So that cancels with those two. And I just realized I missed a coefficient of 2 right here. Okay, good. And then next up, this minus b squared and this minus b squared will cancel with this b squared. Good. And then this minus c squared, this minus c squared will cancel with this 2c squared. Then we can also get a little bit more simplification. This 2bc will cancel with this 2bc. This 2ac will cancel with this 2ac, and this 2ab will cancel with this 2ab. And then next up, we can combine like terms. So this 2ab will cancel with this, or we'll add with that 2ab, 2ac with 2ac, and 2bc with 2bc. So that means we'll have 4 of each of those. So writing that down, we will have 4 times the quantity AB plus BC plus AC, and then that is all squared, and then this is all over 8 times, let's see, that'll be the square root of A plus B plus the square root of B plus C plus the square root of A plus C, all squared, after making our substitutions for X, Y, and Z. I reordered them a little bit just to make it look a little friendlier. Okay, but notice that this 4 squared, but finally this 4 squares to 16, and 16 will cancel with the 8 in the denominator, leaving us with a 2 in the numerator, like that, and then we're left with exactly this right-hand side. So this is equal to the right-hand side of our identity. So through this calculation, we've gone from the left-hand side to the right-hand side. So remember we wrote this general version of this identity. So my question to you is this general identity true? Is it true indefinitely after n equals 3? And can you prove that it's true indefinitely after n equals 3? Or is it false? So maybe post in the comments what you find out. And that's a good place to stop.
Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.